All right. Good morning, everyone. How is it going today? Today I'm going to be showing you how to do a linear regression model in Python. This is going to be pretty much the same tutorial as I showed you before using R, but this time we will be using Python. Okay. Basically, what we're going to be having is an e-commerce dataset with several variables, and in the end we're going to try to predict based on those variables how much a customer is going to spend per year in dollars. Okay, and then we're going to try to evaluate our model to see how well we can predict this data from this data. Okay, so let me just explain to you real quick how this dataset works. So we have the business situation is that we have a clothing store that offers free appointments to their clients with a stylist. Then the clients come in person to the shop. They have this appointment with a stylist. They try out new clothes, etc. And then after a 30-minute-ish session, they can go back home and they can order what they wanted, what they enjoyed. So they can order either from a desktop application or a mobile application. Okay. And we have some other variables as well, and we're going to try to predict from these variables how much that person is going to spend per year. Okay. You can find this dataset on Kaggle. It's very common for studying linear regression. I'll write up a link in the description. Okay. I already downloaded it, so I'm not going to re-download it. It's already here, as you can see inside my notebook file. There you go. So it's this one, ecommerce.csv, and let's just work with this. All right. So there we go. So I'm just going to show you a little bit how the dataset looks like, what the dataset looks like. So first of all, of course, we're going to import the libraries that we're going to use for the analysis. So pandas, we're going to import matplotlib, pyplot splt, and then we're going to import Seaborn as well for some visualization. As SNS. There you go. There you go. So now that we have all our libraries, we're going to have to read our data. I'm just going to do it like this. Just going to do pd read CSV. And then we're going to just write the name of our file. Okay. This time I can just write it like this because the file exists in the same location as my notebook. Okay, but if that's not the case, you would have to find it like here, users, and then here, user, all the path to your file. But here, since it's in the same folder, I can just write the name. Okay, so there you go. Now that we have the file, we can start to look at it and see what it looks like. I print head to see the first elements of the dataset, and here we go. So we have an email, we have an address, we have the avatar, which is probably the name that you use in the online platform. We have the average session length. This is the session that I told you that they spend with the stylist in place. Okay. We also have an average session length, and the average session length. We also have the time on the application, which is the mobile application that they spend before they actually make an order. So when they go back home, they open their phone, they spend, like this person spent 12 minutes in the application, this person spent 11 minutes in the application before actually ordering. Then we also have time spent on the website. We can see that people tend to spend longer time on the website before actually ordering. And we also have the length of their membership in months. So this person has been a member of the store for 4 months, this one for 2 months, 3 months, etc. And this one right here is the variable that we're going to try to predict. It's the yearly amount spent in dollars. Okay, so this person spends $500 $87, $392, etc. Okay. And the way linear regression works is that we're going to take several of these numerical variables, and we're going to create a model that is going to predict how much they spend based only on the numerical variables. Okay, linear regression works with numerical variables to a numerical variable as well. So let's get right into it. To analyze a little bit more how this works, I'm just going to move myself all the way here. To analyze a little bit more how this dataset is structured, we're going to run info right here. And this is going to give us a little bit more information. Basically, just displays the name of the column. So we have email, address, the avatar as I told you, the average session length, time on the application, time on website, just what we saw before. And we can also see the data type, okay? So we know that from the average session length to the yearly amount spent, we have a float 64, which is data type for numbers with decimals. And yeah, so I mean, that basically means that what we're going to be using is this only from column 3 to column 7. So that looks pretty good. Something else that we can do to try to understand a little bit better our data set is we can run this scribe like this. And this is basically just going to give us some statistical information about each of our numerical variables. So as you can see, we have, I mean, you can see that here as well, 500 observations. We have 500 observations for each of the variables, of course. And then we can see the mean for each one of these. For example, the average session length, as I told you that it's 30 minutes-ish for everyone. So the mean for that is 33, and you have a standard deviation of 0.99, which means that mostly it's very, very close to 33. Same, the time on the application is 12, the time on the website average 37, we have a minimum of 33, minimum of 8, etc. Okay, so I mean, this is basically just to give you an idea of how much of each of the numerical variables. And this is very important as well to check this after you have done your model construction, to actually know that what you are getting actually makes sense. So for example, here you have that the yearly amount spent, you have a maximum of 765, a minimum of 256, and an average of 499. If your prediction returns that someone's going to spend like 2000 for similar session length and time on application, etc., I mean, you probably want to check again your model because there might be something fishy about it. But yeah, I mean, this is basically how it works. So let's just start doing some EDA, okay? Some EDA, exploratory data analysis, okay? I'm just going to guide you through some plots so that you can compare different variables together. And we're going to be using Seaborn, which I imported up here before. And for Seaborn, we're going to use a joint plot right here, joint plot like that. Okay. Basically, it takes some arguments. It takes an X argument that's going to be the variable that's going to be plotted on the X-axis. And for this one, we're going to use time on website. I'm just going to copy it from here so that I don't make any mistakes, any spelling mistakes. And for the Y, we're going to, of course, use our target variable, which is the one that we're going to try to predict. And then as data, we're just going to say that our data is our df variable. There you go. Then let's run it, and here we have it. So as you can see, a joint plot is basically a scatter plot, which makes 1 point for each observation. And it also creates a histogram of the variable on the other side of the axis. So that's pretty convenient. That gives you an overall view of the relationship between two variables. Here you probably cannot see it extremely clearly because I mean it's many points are cluttered together and clustered here, so you don't really see how many there are actually. So a good thing that you can do is that you can pass in an alpha argument like this. So now you're passing a parameter of alpha, and that basically means that each point is going to have an alpha and opacity of 0.5, which basically means that the more points are on the same place, the darker it's going to look. So here you can see it's very faint, and here you can see that it's starting to be a little bit more dark. So basically means that there are more points right here. It's just easier to visualize the concentration of points. So there you go. This also allows you to see if there is any relationship between the two. I don't see any correlation here. I mean, it's not very easy to see, but let's test another two variables. Okay, I'm just going to copy this code right here. And instead of using time on website, I'm going to say that the time on application. Remember that right here, I am passing the name of the variable, and the name of the variable is time on app. Okay, that is why I can write it like this. Just going to run it. And as you can see here, you have a little bit more of a correlation. We have time on application from 0 to 15 minutes, as we had seen before. And you have the yearly amount spent, and you can see a faint correlation in which the more time people spent on the application, the more money they tend to spend on the year. Okay, so that's how you do pairplots. It's very convenient to compare two variables. I'm going to show you joint plots. I'm going to show you how to do a pairplot this time. Okay, pairplots are a little bit more a little bit heavier because they compare all of the numerical variables at the same time. So if you are just starting out your analysis, you might want to do this one, but try not to overload it with 100 numerical variables, because it's just going to give you too many plots to actually visualize. So this one right here works pretty good right now because we don't have so many numerical variables. So I'm just going to pass in our data. And then I'm going to say that the kind of plot that I want is a scatter plot. And there we go. Let's just pass in this argument right here. Let's set an alpha again. Let's set an alpha of 0.4. All right, let's see how that looks. Pairplot, not pairlot. All right, what's the problem here? This is supposed to be an S. There you go. All right, there you go. So basically, here we have just what we had before, but it's comparing all of the variables at the same time. And if at some point you have the same variable against itself, it just creates a very simple histogram. Okay. This is basically just to add the alpha, as I told you before, so that you can visualize the concentration of points a little bit easier. So there you go. You have the correlation between time on application, for example, against average session length, etc. Of course, what we are interested in is basically the last line right here, or this last column right here, which are the ones that talk about the yearly amount spent, which is our target variable. So you can see that there is a faint correlation as well between the yearly amount spent and the average session length. Time on website doesn't seem correlated at all, as we had seen before. There seems to be a lot of correlation with the length of membership. So, I mean, this is basically just to give you some general idea of what is going on. All right, so once that you have understood a little bit better what is going on with your dataset and how it behaves, and your variables, how some correlations are expressed and some correlations are don't seem to be very important, we can actually start building our model. Okay. All right, so let me show you real quick what is actually going to happen during the model. Okay. To do that, I'm just going to write a single plot right here, which is going to make it a little bit easier to visualize. This one's called LM plot, which is linear model plot. And it's very convenient to actually visualize what is going on. So I'm going to plot the length of membership this time. This is not supposed to be a comment. Length of membership, like this. And that's an X. Now for Y, I'm going to plot yearly amount spent. And then the data is of course going to be RDF, like that. And then just as before, I'm going to add an alpha right here. No, the alpha scatter like this, and then we add an alpha right here. This is basically when you have like a little bit more of a complex plot. You sometimes have to use this kind of parameters to actually set up the alpha. But there you go. I think that's all. So let's see how that looks like. There you go. Okay. So here, what is going on is very simple. We have the scatter plot that we built right here. Okay. And so what we're going to do, basically imagine that we only have two variables. Okay. This is a very, very basic explanation of linear regression. Imagine that we only have two variables. We have the length of membership and we have the yearly amount spent. And you see that there's a faint correlation, like a strong correlation between these two. All right, so what we're going to do is we're going to ask the computer to create a line right here. That line is, in the first time that it's going to create the line, it's just going to write a very random line. It might be somewhere right here, a 1 to 1, etc. Okay, and then once the line is created, it's going to start measuring the distance from each point to the line. Okay, so here you have one distance, here you have another distance, here you have another distance, and it's going to square them. Like this one, say it's 12. This one, say it's 15. This one, say it's 40. And it's going to square that distance. That means that the bigger the distance, the bigger the square. So bigger distances are going to be more penalized than smaller distances. Okay, so basically it's going to measure the distance between the line and every single of these dots. It's going to add them all together, and then it's going to tilt the line a little bit, and it's going to continue doing that until the sum of all of these distances, of these square distances, is the minimum possible distance that you can get. That's, other way of saying it is that it's going to create a line that is as close as possible to every single point in the scatter plot. Okay, and that's basically what a linear regression is for two variables. It's just trying to create a line that gets the least sum of squares of all of these dots. Now imagine that that's what we're doing with two variables. Now imagine that we want to predict how much someone's going to spend if they have 6 months if they have been a member for 6 months. And what the purpose of this line is that you're going to go here and you're going to check and you're going to see, oh, okay, so this person has been a member for 6 months, so it's going to be somewhere right here, and then you're going to calculate the value of your function right here, and it's going to be probably 640 or something like that. So you're going to predict that it's going to be 640. That's all that is going on with a linear regression. And as you can see, it might not be perfect, but it's pretty close to actual values. So it's a good enough model to do predictions. Now, this is with only two variables. Now, imagine you are doing exactly the same thing, but with more than two axes. So you can add a third variable right here, and you have like scatter plots in a 3-dimensional space, and you have a line that is passing through them. Okay, so all that we're trying to do is find the equation. The equation that describes this line in two dimensions, in 3 dimensions, and in n dimensions, right? So that's basically, very basically what's going to be doing this model that we have right here, which we're going to import from Scikit-Learn, okay? So to actually apply that, we're going to add Scikit-Learn, and then we're going to add it from model selection. There you go. And then from here, we're going to import train test split. All right. What we're going to do right now, basically with this function that we have just imported, is we're going to take all of our data and we're going to divide it into a training set and into a testing set. Okay. The reason why we're doing this is that we want to take, let's say, 70% of our data, and we want to show it. I mean, we want to create this function that is going to predict the value of the yearly amount spent, but we don't, and then we're going to have to test it, of course, to see if our predictions of this function are correct. But we cannot test it with the same data that we used to create the model. So that's why we're just creating a different data set, a different portion of the data set to test our model in. So basically what we do here is we're going to say that we're going to have 2 sets. The first set is just going to be all of our predictive variables, okay? Which basically is all of this right here. Let me just copy this for you. There you go. So we're going to have our data set, and remember that to choose a certain set of columns, you can just say, all right, so I want the time on app. This is basically just going to just show you. This is basically just going to select all of the time on the application, all of the values in the time application column. If you want more than that, you can pass a list with the names of the columns like this. So you can say the time on application, and you want the time on website too, like this. There you go. So, what is going on here? Yep, didn't close it, like that. So now you have time on app, time on website, and you have a different data frame with time on application and time on website. What we're going to do right now is we're going to create a data set with all of our predictive variables without the target variable. The target variable is, of course, the one that we're trying to predict. And our predictive variable is basically just going to be yearly amount spent, like that. So there we have it. We have our predictors and we have our target. And now what we're going to do is we're going to use this one right here to make the split into our training set and our test data set. So to do this, we're going to create a variable called xtrain, one called xtest, another called ytrain, and another one called ytest. Okay. Remember that in Python you can just initialize several variables at the same time just by separating them with a comma, as long as your function is returning several variables as well. So that's basically what this function right here does. It returns 4 values, one for train, one for test, one for the predictors for train and test, and one for the target for test, for train and test. So there you go. So you have the train test split. The first argument that you're going to pass is the predictors, and the second argument that you're going to pass is the target variable. Then you're going to just set your test size. Basically, this means how big your testing, how big how big is going to be the training section, the testing section of your dataset. Okay, so we're going to train on 70% of the dataset, and we're going to test our model on 30% of it. So let's say 30%, which is 0.3. And then after that, we're going to set here a random state. Right here, this argument is basically just any number. I mean, whichever number you want to add right here, it really doesn't change anything. The idea behind this is that if you ever want to reproduce, I mean, you're creating a random split, okay? So if you ever want to reproduce the same split, you're going to have to pass in the same number. So that's basically all that we're doing. So that means that if you pass in here 1, and if you sometime want to reproduce this same split, you're going to have to pass the same data and the same number 1. A good rule of thumb is to always go for 42, because that's the answer for everything. There you go. So now basically we have just created our 4 variables. Let me show them to you. Xtrain. Oops. You might be wondering why X is an uppercase and Y is lowercase. That basically is just to mimic mathematical language in which uppercase variables are often express several, a matrix of several other variables, and lowercase variables express just a single value. So here, since X represents several predictive variables, it's in uppercase, and Y, since it represents just one variable, it's in lowercase. So you can see that here we have Xtrain, we have 350 rows, and we have our numerical variables. Then we have, let's see, Xtest. We have exactly the same number of columns, but we have only 150 rows, because this is the number of rows that we're going to, this is the number of observations on which we're going to test our predictions. Same with Y. We have Y test, which is 150 values, and Y train, which is 350, right? Basically, that's our split. So there you go. Now, we're going to actually train our model, okay? Let me just write right here. Training the model. There you go. Okay, so to train the model, we're going to also use Scikit-Learn, and we're going to do from Scikit-Learn. Scikit-Learn, in case I didn't mention it before, is just a library with many machine learning models that you can just import and use. It's as simple as what I'm doing right now. You don't have to actually build the model. It's built for you. So linear model, and we're going to import linear regression like this. So now we have imported Scikit-Learn. Now what we're going to do is we're going to basically just initialize an instance of this model like this. Linear regression. Oops. Here we're just calling the function that we just imported. Let's run this. So there we have it. Linear model. This is our model. And now from this linear model, we're going to want to fit the data to it. That basically means that we're going to train it. Okay. So let's see. LM fit. We are going to pass in Xtrain, which is the training portion of our dataset. And then we're going to say Y train. Basically, we're just selling it. All right. So given these variables that we have right here, every time it should return this thing. Okay. So given this X, you should return this Y, and it's going to try to find this, the equation that is going to predict this function right here. There you go. So now, oops, what is going on? Yeah, there you go. So basically we have now created our data, our model, and we have trained it. All right. So now something important right here. Now we're going to have to take a look at our coefficients. Okay. So basically, let me just show you what it means. lm.fit, lm.coef, like this. This basically just returns all of your coefficients. But what are coefficients in a linear regression model? All right, so let me show you linear regression formula. All right, so basically, let me see if I can find a little bit easier formula to visualize. Actually, I had one on my Medium thingy. All right, so basically a linear regression is just this formula right here. Okay, so I mean, for any line in a two-dimensional plane, you can describe it using this formula. It basically is that your predicted value is going to be some intersection with the x-axis, which in this case is somewhere around 200 and something-ish, plus a coefficient, that modifies your x, that like weights your x value, okay? Your x variable. And the more variables you have, the more coefficients like this you have. So basically, this coefficient is going to tell you how important your variable is. And here, right here, you have the coefficients for each of the variables that we have created. So let me show you this real quick. To show you how the coefficients look, I'm just going to do this like this. PD, we're going to create a data frame from our coefficients that I have just showed you, coef, like this. Then you're going to take x.columns, and the columns are going to be equal to coef, not coed. Then let's just print it. Let's see how that looks like. All right. So basically, I just run the columns as observations, and then created one column for the coefficient. And this coefficient is basically this right here. This just gives us how important each of the variables is to our model. Okay. So basically, instead of having just a simple linear model with one variable, we have a multiple linear model with multiple variables. So we have our target value variable is predicted by a coefficient of the intersection with 0, and then we have one coefficient for the variable 1, one coefficient for the variable 2, one coefficient for the variable 3, and all the way until n variables. Here we have 4 variables, so these are the coefficients for each one of them. And of course, each coefficient, I mean, the higher the coefficient, the more important the variable. So here we can see that the variable that is actually having the greatest impact on our target variable is length of membership, which is 61. Then the next one that is important here is the time they spent on the application, and then we have the average session length. All right, so what we're going to be doing right now is basically we're going to use this model that we have just created using this equation that basically is just a relationship between x and y, all the x's and y with different coefficients, and we're just going to use it to create some predictions for our data. Okay, so let's just write it down right here, predictions. Of course, I'm going to leave this notebook on the description so you can check it, and I'm going to add some other titles so that it's easier for you to actually follow through the notebook to see what's going on. All right, don't forget to like the video, of course, please. That helps a lot. And all right, so the predictions, for the predictions, we're going to store them in a variable called predictions. And basically, we just run this method on our model that's called predict. Predict, like that. And basically, we just give it some values of x that we want to test in. Now, if you remember, we had previously created a test x section, subset of our dataset that we were going to use to test. So we just give it to it like this, x test, like that. And basically, this is just going to, let me show you. this is just going to return an array with all the predictions that of what it thinks it's going to be the Y column, the target column, which is the yearly amount spent, based on the X that we gave it. Okay, so that's basically all that it's doing. It just returned the column on the left side. All right, so what I'm going to do right now is we're going to create a scatter plot to see the actual values, because remember that we had a Y test as well, which is the actual values of those variables. So what we're going to do right now is we're going to try to plot this predicted variables against the actual values and see if they form some sort of straight line, because if they form a straight line, that means that our predictions are rather accurate, because if the prediction was 200 and they actually spent 200, that's going to be a one-to-one relationship. And if it's a one-to-one relationship in every single case, then it's just going to create a straight line of one-to-one. Okay, so let's see how that works. Basically, I'm just going to use Seaborn again to do this. I'm going to do a scatter plot, and on the x-axis, I'm just going to say that let's add the predictions on the x-axis, predictions, and on the y-axis we're going to add the actual y value, which is y test. Yeah, I think that's how it goes. Yearly amount spent. I'm just going to add another name right here. PLT. Let's add an X label of predictions. This basically is just going to add this label right here that is going to say that it's a prediction. There you go. So here you have predictions and the yearly amount spent. You can also, of course, you can add a title if you want. Evaluation of our linear regression model. So there you have it. We have a title, and as you can see, our predictions, if at some point the prediction was 400 and our actual value was 400-ish, that basically means that our model seems to be rather good. As you can see, this sort of creates a straight line. So our model seems to be behaving rather good. Let's just make some other measurements to see that it actually works. Okay. Scikit-Learn actually comes with a set of evaluating methods that you can apply to see how your method did, and that's basically what I'm going to do right now. Let's import from Scikit-Learn scikit-learn.metrics, and from there you're going to import the mean squared error and the mean absolute error. Okay, and let's import math as well, because we're going to do some operations as well. And basically, I'm just going to ask you to print the mean absolute error. If you don't know what these things are, you probably want to look them up. I'm just going to explain them real quick. But let's just show you this real quick. Okay, so we can use the mean absolute error of y test and the predictions against the predictions, like that. And then instead of the mean absolute error, we're going to use the mean square error, like this. And then here we're going to use mean squared error. And then the last one is actually going to be the root mean squared error. Root mean squared error, just like that. And actually, I don't think there's give a function out of the box for this one, so I'm just going to do this like real quick. Like I'm going to use math. So actually, I have the formula right here. I'm just going to copy it real quick for you. There you go. There you go. Okay, so basically it's the square root of the mean squared error. Yeah, so there you go. All right, so let's see how that looks like. So the mean absolute error is basically the average distance of every point to the actual line, okay? So remember that we had this line right here that it describes our model, and then we have several points around it. Basically what we're doing here is we're saying, so what is the average distance between this line and the closest point? And the point that it's supposed to predict. So the average distance is 8 units, and that's very telling because the mean absolute error actually is in the same unit as your variable, so which means that this is $8, and a mean error of $8 is actually pretty good, considering that our yearly amount spent usually lingers around $500. So an error of $8 in an $800 prediction, in a prediction of a value that usually is between around 500, it's actually pretty good. We have a mean squared error as well, which is 103. This one basically is the same thing as the mean absolute error, but every time that there is a distance between the predicted value and the value and the real value, you square it. So you take the square of it, which basically means that the longer, the bigger the distance between the predicted value and the actual value, the more it's going to be penalized. Okay, so if you have a distance of 1, the square error of that one is going to be 1. But if you have an error, and that's going to be considered into the error. But if you have an error of 10, then it's going to add 100 to your metric, and that's just going to. You can see that the bigger the error, the more important it is. And this one is basically this one is also in the units in the original units. So I would say that this model seems to be looking pretty good. Something also that is pretty important that we need to do is we need to analyze the residuals, okay? So, linear models, like linear regression, usually assume that the residuals of your predictions is going to be normally distributed, okay? Which basically means that your residuals, which is what I told you, the distance between your model prediction and the actual value, are supposed to be random. If they're random, then they're supposed to fall on a normal distribution. So let's see how that works. So we have the residuals, which, as I told you, is basically just the actual values minus your predictions. That's all there is. So the first thing that we're going to want to do is we're going to plot these residuals and see how they're distributed, okay? The easiest way to do this is to create just a histogram with all of your residuals and see how they fall into the distribution, okay? This we can do it using Seaborn. So basically I'm just going to use SNS distplot like this, and I'm going to pass in the residuals, which is basically, let me just show you real quick what the residuals look like. Okay, so as you can see, it's basically just the distance between the predicted value and the actual value for each observation. So for observation 361, the predicted value was something and the actual value was something else, and the distance or the difference between these two is it's 2.63. Okay, so yeah, there you go. Now what we're going to do is we're going to test for normality, because linear models actually assume that if you are using linear models actually assume that if you make a prediction using linear regression, the residuals, which is this distance of the things of the actual prediction and the value, the residuals are supposed to be random. If they are not random, that basically means that there is something sketchy about your about your model, and it's biased towards something. So if your residuals are completely random, that basically just means that the errors come from nowhere, but from just the statistical statistical errors that are normal to find in any prediction. Okay, so in order to test for these errors, what we're going to do is we're going to write we're going to create this histogram. So to do that, we're going to use the display that I mentioned before. I'm going to plot the residuals like that, and let's see how that looks like. All right, this is starting to look pretty normal. I mean, there is some sort of a tilt there's some sort of a skew on the left side, but I think it could qualify as a normal distribution. Let's just augment the number of bins that we have here. So we have 30 bins. Bins basically means how many of these bars we're going to be creating. So the more bars, the less clear the actual distribution is. So, you can play around with it just to try to find some bin number that actually it is easier to visualize for you. And then if you want to actually plot the distribution right here, we can use KDE and just set it to true, and it basically is just going to add this line that's going to allow you to see the curve that is going to allow you to basically see a little bit better if it's a normal distribution or not. Another graphical method to test for normality is to create a QQ plot. Okay, I'm not going to go into the details of what is a QQ plot, because the video is already getting quite long and it's not the objective of the video, but basically it's a plot that you have normality on one side and you have your residuals on the other side, and if it creates a straight line, if it's 1 to 1, it basically means that your residuals are normally distributed. So let's see how that works. We have SciPy and stats that we're going to import, and we're going to import it as stats like that. And then from stats, what we're going to do is we're going to call probability plot like that, and we're going to pass in the residuals. The distribution that we try to test for is normality, and let's say that we want to plot it using Pylab like that. There you go. And we just do pylab.show. There's not supposed to be two T's here, and residuals is actually spelled with an E, not an A, of course. And normal, no, it's not supposed to be normal, it's norm. Alright, sorry about that. There you go. So there you have it. You have your probability plot. Basically what I told you is that if it's normally distributed, it's going to approximate the straight line as much as possible. So this looks good enough. There are also some analytical methods to test for normality, but we can discuss that in another time. Alright, so I hope you found this useful. I hope that you enjoyed something, that you learned something from it. And yeah, the applications for this are huge. You can of course be doing just a linear regression for your company based on some data set that they give you, and you just give them some predictions. But also, the big power of this kind of models, of them being automated like this, is basically that you can run this in a server and connect it to a web application, for example. So, there are several, we're using Python here, and there are several backend technologies for servers. And if you see that there's very little code involved in this prediction. So if you train your model, and once your model is trained, you put it up on your server, you can basically use it to make predictions. If you connect it to a web application, and then it can basically just return your prediction using this test. So that's basically all the power that comes with it being so simple and so automated in Python. Alright, so I hope that you found this video useful. I hope that you learned from it. Please leave a like if you enjoyed it, and yeah, follow and subscribe for more. And I'm gonna be putting up some more machine learning models and explanations for you, probably some web technologies as well. Alright, so I'll hope to see you next time. Ciao.